up until now, we've been looking at systems whereby the primary refrigerant has actually been running through the space that is in direct contact with the area being cooled. This last section, before it leads on to heat pumps, looks at indirect refrigeration systems, which is actually very similar to the process of heat pumps, or it certainly leads into it. So basically, an indirect refrigeration system is one whereby the primary refrigerant is away from the actual space being cooled, and there is a secondary circuit where a different refrigerant is being circulated through, and the heat that is being transferred into the secondary refrigerant is cooled through a heat exchanger that is incorporated in the actual evaporator of the primary circuit. So looking at the diagram there, in the green you've got the primary circuit. That is where the more volatile refrigerant is being circulated. And then you've got the secondary circuit on the right hand side, which is circulating either water or an antifreeze solution by means of a pump. The difference between the two are, in the primary circuit, the refrigerant is constantly being evaporated and condensed, whereas in the secondary circuit, the actual phase of the secondary refrigerant remains the same, i.e. it is constantly a liquid, although the heat is being transferred in and out of it. It doesn't actually evaporate or condense. The advantages and the disadvantages of using a secondary refrigerant loop are listed on page 19 here. There may be times where by means of the design of the system you do have a choice as to whether to have a direct system or whether to have the secondary refrigerant. Other times it's just simply not feasible to have the primary refrigerant circulating around the whole system and being in direct contact with the spaces being cooled. But if you can have a read through these and have a look at the actual diagram again on the previous page, on page 18, just to give you, and read the text there to give you a bit of a fuller understanding of an indirect system. On the next page there's a diagram, an example that takes us through how to actually calculate the energy transfers and so on in the system, taking into account the fact that we now have this secondary refrigerant circulating separately to a primary circuit. So looking at an example of a secondary refrigerant system, we're told here that the plant is using ammonia as the primary refrigerant and a brine solution as the secondary refrigerant, and that secondary refrigerant is circulating around 3 separate cold spaces, as is shown in the diagram at the bottom of the page. We're given, first of all, conditions in the primary circuit. So we're told the condenser pressure is 880 kilopascals. At the condenser outlet we have 20 degrees Celsius. Our evaporator pressure is at 250 kilopascals, and our outlet temperature of the evaporator is 0 degrees Celsius. We're given an isentropic efficiency of compression as 82%, and an electrical mechanical efficiency of the compressor of 85%. So with that information we can actually plot the cycle diagram on our pressure enthalpy chart. We're told that at exit from the evaporator was 0 degrees and we're also given the pressure. So the first thing you can do is to draw your horizontal pressure lines, locate 0 degrees at exit from the evaporator, assume constant entropy initially. That will take us up to the ideal enthalpy value at exit from the compressor. We're also told that at exit from the condenser it was 20 degrees, so again we can now locate our vertical line through throttling. the first thing to do, having drawn the basic cycle, is to calculate the actual enthalpy at exit from the compression process, H2. So having listed the enthalpy values from the chart for H1, H2 dash, H3 and 4, then if we apply an equation for isentropic efficiency of compression, then we get again our ideal work input over the actual, H2 dash minus H1 over H2 minus H1. So again, transposing that equation for H2, then we get H2 dash minus H1 over efficiency plus H1. If we input all these values, then we get our actual enthalpy at exit from compression as 1680 kilojoules per kilogram. So now that we have all of our enthalpy values, we can go ahead now and just answer the questions. Now you'll note from the bottom of page 20, the equation for the heat transfer in the secondary circuit, and we've come across this before. It's MCP delta T. MCP delta T, mass flow rate times specific heat capacity at constant pressure times change in temperature. And we're going to apply that equation in evaluating the amount of heat ingress into each of the three cold spaces. Now we're also told that in the pipework that takes the secondary refrigerant around the circuit, it also absorbs a further 13 megajoules per hour of energy. So basically what that represents is the heat leakage into cold space 1, 2 and 3 plus the heat leakage into the refrigerant in the pipework system and so on is going to be equal to the amount of heat that needs to be removed from it by the primary circuit in the evaporator. So then to answer part A, which is the total heat transferred from the brine in the evaporator, then it's going to be equal to the sum of the heat being removed from each of the cold spaces, 1, 2 and 3, plus the heat energy being having to be removed by the ingress of heat in the pipework system and so on. So we need to change our megajoules per hour into kilojoules per second so that we're equivalent to the rest of the equation. So to do that, then just change megajoules into kilojoules by times it by 1,000, and then changing hours into seconds by dividing by 3,600, and that gives us our 3.61. So if we list our MC delta T equation for each of the three cold spaces, 1, 2 and 3, then this is our full equation to calculate the total heat energy being removed from the secondary circuit in the evaporator. And just to remind us of the conditions in the actual secondary circuit, we're told that we're given the information here for the three cold spaces 1, 2 and 3. So we're told that the mass flow rate for each of the three spaces are 1 kilogram per second, 0.8 and 0.6 respectively. We're told the inlet and outlet temperatures of each of the three cold spaces, again listed here, and we're going to use all the information, as well as the CP value for the brine. So this is our CP value that we're going to use in the equation. So we're going to put all this information into our equation for the heat transfer in the evaporator, in which case we get all of this, and a value of 61.43 kilowatts for the total heat transfer in the evaporator, the heat transferred from the brine in the primary circuit. So the second question was to find out the mass flow rate of the refrigerant. That is the mass flow rate of the primary refrigerant. So we're applying an equation again, change in enthalpy times mass flow rate of refrigerant. This value here we've just worked out to be our 61.43. We already have our H1 and H4 from our pressure enthalpy diagram, so it's a simple case of transposing for the mass flow rate of refrigerant, in which case we get 0.0521 kilograms per second. To calculate the compressor electrical power, we need to first of all calculate what the work done in the compressor is, and we'll do that as before using our mass flow rate times the change in enthalpy. So we have all these values now. For mass flow to refrigerant, we have H2 and H1 from a chart, so we get 11.56 kilowatts. So we're told that the actual mechanical electrical efficiency of the compressor was 0.85 or 85%. So again, applying an equation for efficiency to the actual compressor, then we get power output over power input. The power output we've just calculated to be 11.56 kilowatts. We want to find out what the power input is. So equating that to our 85% and transposing for power input, we get our actual power input to the compressor based on our electrical mechanical efficiency of 13.6 kilowatts. The next part of the question, question 2a, is asking us to calculate the mass of air that could be heated by the heat being rejected in the condenser if the air is to be raised by 15 Kelvin, 15 K, and we're given a heat capacity of the air as 1.005 kilojoules per kilogram K. So if we first of all calculate what the actual heat transfer is in the condenser by applying an equation from the primary circuit using mass flow rate of refrigerant times change in enthalpy, we get 73 kilowatts. And if we then apply our MC delta T equation, the same equation we applied to the secondary circuit earlier, but this time it's under the conditions of the air being heated by the heat being rejected in the condenser, then we get MCP delta T as it applies to the air using the 73 kilowatts we've just calculated. Transpose for the mass flow rate of air, keeping in mind our temperature difference of 15, and we get 4.63 kilograms per second. Lastly, we're asked to calculate what the coefficient of performance would be if the system is being used as a combined refrigerator and heat pump. That means that in terms of useful energy, both the heat being absorbed in the evaporator and the heat being rejected in the condenser is useful, in which case our coefficient of performance equation is equal to the total heat transfer divided by the work input. And if we input our values from earlier, we get a coefficient of performance of approximately 10. That value is obviously very high. It is an ideal value, and it is based on all of the energy being transferred in both the condenser and the evaporator being expressed as useful energy. The last section of the teaching pack, section 5.1, looks at the use of heat pumps. Now basically a heat pump is a device that takes advantage of the solar energy that's stored either underground or the solar energy that's present in the air, and it extracts energy from that low-grade source. It transfers that energy into the heat pump, where it's upgraded by means of a compression process, and that upgraded energy is then passed usually into either water or air used to heat a building space. Now, as I said before, these devices are becoming more and more common. The performance of these systems vary greatly depending on the actual application, depending on location, ground conditions, air conditions, and so on. Comparing air source heat pumps and ground source heat pumps, obviously the temperature of the air is constantly changing, whereas the temperature in the ground is below a certain level is constant, which is good, because it means that you can design the heat pump more accurately. You do obviously have to be careful in terms of the rate at which you're extracting the energy from the ground, in that if the extraction rate is higher than the rate that the heat can be replenished in the ground around your reference loop, then you mine the heat, and your heat pump is then having to work harder and harder, and therefore your coefficient of performance is dropping off, and you're paying more to run the heat pump. But even in locations in Scotland, you can expect coefficients of performance. Uh, 300% would not be unusual. Again, it varies depending on your location and so on. It depends on the ground conditions as well. I mean, ideally, if you could have your reference loop in running water, for example, or certainly in ground that is moist and ground conditions that encourage the rate of heat transfer, then that's going to be a more efficient system. Whereas if you have a very dry ground, a dry soil that has air pockets in it, then obviously there's more resistance there to the rate of heat transfer through the ground and into your reference loop. So basically the heat pump, it actually has three loops in it. You have the primary circuit, which is your heat pump, where the refrigerant, the volatile refrigerant, is circulating. You have the ground-based reference loop, where you have the secondary refrigerant circulating, similar to what we covered in indirect refrigeration systems. And then we have the heating loop, which contains either the air or the water that is taking the heat energy from your primary refrigerant and transferring it into the actual building space. So the diagram on the next page shows that these three loops. Over on the left hand side you have the ground-based secondary loop. So this is going to contain probably a brine solution that is circulating through the ground. It's absorbing heat from the surrounding area. That heat is then taken, it's pumped around the system into the evaporator, where the heat is transferred from your secondary refrigerant into your primary refrigerant. So that causes the primary refrigerant to boil. That is then taken into the compressor, it's upgraded and passed through into the condenser, where the energy, the heat energy that's now in your primary refrigerant is passed into the heating loop, and that in turn then is passed out to the heat exchangers in your rooms, whether that is conventional radiators, oversized radiators, underfloor heating, whatever. And then your primary refrigerant moves out your condenser through your expansion valve, where it's expanded and cooled, and then the system just keeps on going like that. Now, obviously, there are the additional losses and work inputs. For example, in the pump circulating the brine, there needs to be a pump, of course, in the heating loop, as well as the compressor in the primary refrigerant loop. All these things obviously contribute to the overall coefficient of performance. And again, that's going to vary depending on the application and depending on your ground-based secondary loop. Again, you can have pipes that are buried horizontally down to a meter or a meter and a half, or you can actually have vertical boreholes. And again, the amount of heat that can be recovered from the ground in these systems varies. With the vertical systems tend to be more efficient. However, you have to balance that against the increased cost of actually doing the vertical boreholes, which can be very expensive. So it's all about weighing up when you're in designing the system. It's all about weighing up the running conditions, the actual demands on the heating system, the ground conditions, and so on. All these things will be taken into account in designing one of these systems, as well as obviously thinking about the rate at which heat is being removed from the actual secondary ground source. The example at the at the end of the teaching pack, example 7, shows a heat pump that is using R12 as the refrigerant, and it tells us that at entry to the compressor the refrigerant is at 0 degrees, and at exit it's at 80 degrees Celsius. The condenser produces saturated liquid at 50 degrees, and at the end of the throttling process the temperature of the refrigerant is minus 10 degrees Celsius. we're given the flow rate as 0.02 kilograms per second, and we're also given the mechanical electrical efficiency of the compressor as 80%. So we're asked to find, having plotted the system on a pH chart, we're asked to find the coefficient of performance based on compressor indicated power. In other words, using the efficiency, mechanical electrical efficiency. The coefficient of performance if there is 5 K of undercooling at the condenser exit, and then finally the temperature at exit from the compressor if we assume that the compression process is isentropic, reversible and adiabatic in other words. So looking at the chart, the first thing to do would be to locate the temperatures in the condenser and an evaporator, which we were told were 50 degrees Celsius for the condenser and -10 for the evaporator. So if you locate these temperatures along your saturated liquid line and then draw the horizontal lines across your chart, the next step would be to locate the conditions of the refrigerant at exit from the evaporator and therefore entry to the compressor, which we were told was at 0 degrees Celsius. So that enables us to locate point 1. We were told that at exit from the compression process, the temperature of the refrigerant was 80 degrees Celsius. So again, that enables us to locate point 2, and that would be the actual enthalpy at exit from the compression process. Because, as you can see, between point 1 and point 2, there has been an increase in entropy. We can also plot the ideal enthalpy at exit from the compression process by simply following a line of constant entropy, and that enables us to locate point 2 dash along our condenser temperature line. Finally, we can draw a vertical line down from the point where at exit from the condenser at 50 degrees we have saturated liquid, and down vertically until it intersects the temperature line in the evaporator. So that completes our chart. Question B is going to ask for the coefficient of performance if there is 5 K of undercooling. So all we need to do there is to take our point 3 to the left until it intersects the 45 degree temperature line, and then project that down to our enthalpy line at the base of the chart. So taking all of these values from the chart, we get an enthalpy of H1 of 190, H2 of 230, H3 for part A as being 84 kilojoules per kilogram, and for part B we get an enthalpy of 80 kilojoules per kilogram. So first of all, we're asked to find the coefficient of performance based on the indicated power. So if we apply an equation for the efficiency, electrical mechanical efficiency of the compressor, then we get work output over work input. If we transpose that for our work input, that gives us, using the efficiency, the mechanical electrical efficiency of 80% or 0.8, we get our work input of 50 kilojoules per kilogram. So applying it now, our equation for the coefficient of performance for the heat pump, then it is the heat transferred in the condenser divided by the work input in the compressor, and if we input our values from that we gain from the chart, using the calculated value of 50 kilojoules per kilogram, we get a coefficient of performance of just under 3. Part B is when there is 5K of undercooling. So we're now using our 80 kilojoules per kilogram as opposed to 84, and that gives us a coefficient of performance of 3. And question C is asking for the temperature at exit from the compressor if the compression process is assumed to be isentropic, and again going back to our chart and reading off the value at exit from the compressor, assuming the line follows the constant entropy line, we get 69 degrees Celsius. So that takes us to the end of the refrigeration and heat pump cycles teaching pack. The solutions, as I said before, you'll find at the end of the teaching pack. And once you work your way through this teaching pack and through the commentaries and through the SAQs, you're then in a position to, if you haven't done so already, to begin your coursework. And as I've probably already said in some emails sent to you, the next topic we're going to be looking at is vapor power cycles, which is going to be made available to you shortly. So you should really be in a position to have completed the refrigeration and heat pumps materials, certainly by the end of this week, which frees us up then to begin looking at vapor power cycles.